This is part 7 of a series on decision trees. In this video, we will write code to build a CART classification tree. In the last video, we learned how to use the Gini index and information gain to find the best split point and build an optimal CART tree. In this video, we'll implement a CART classification model from scratch in Python based on what we've learned so far. Then, we'll compare our results with those from scikit-learn's Decision Tree Classifier to see how well they match. Since this code builds a binary tree recursively from scratch, it may be a bit challenging for beginners in machine learning. If you're a beginner, I recommend using scikit-learn's Decision Tree Classifier. But if you want a deeper understanding of the CART algorithm, this video will help you. First, we define a node class to store the key information for each node in the tree. A decision tree consists of split nodes and leaf nodes. For each split node, we store the feature index and split point used to divide the data, along with references to the left and right child nodes. If a child node is not a leaf node, it contains the data indices assigned to that node. For each leaf node, we store the final predicted class label. Next, we'll implement the MXML-2-07 class. This is a CART-based Decision Tree Classifier that builds a binary tree. This class takes the maximum depth of the tree as input. The uClass variable stores the unique class labels in the target variable y. The feature and target variables store the training data features and target classes, respectively. When the fit function is called in this way, xtrain is assigned to the feature variable, and ytrain to the target variable. The training data, xtrain, is structured as follows. Consists of m features and n data samples. Each feature is identified by its ID, fid, and each data sample is identified by its ID, did. Now, let's go through the functions in this class one by one. First, we define a function that calculates the Gini index of a given node using the following formula. Since we've already covered this formula, I'll skip the explanation. Next, we define a function that splits a parent node into left and right child nodes. The parent node contains the indices of the data samples. For example, it contains data point IDs such as 0, 7, and 3. Among them, 0 and 3 go to the left child node, and 7 goes to the right child node. The number of samples in the parent node is n. First, we calculate the Gini index for the parent node. Next, we evaluate all candidate split points across all features and select the best feature and split point based on information gain. To find the maximum information gain, first initialize the max IG variable to a very small value. Then we take each feature from the training data and extract the feature values for the samples indexed by did. If this is the list of data point IDs in the root node, and the feature ID is 0, then xfeat will be the following column vector. Now we need to find the best split point within xfeat. Remove duplicates from the xFeet vector and sort it in ascending order. This gives us the xUnique vector. For example, suppose the unique feature values are as follows. Then, the averages of adjacent values are used as candidate split points. This gives us the S-points list. Next, we take each split point P from the S-point list and split xFeet into left and right child nodes at P. Data points less than or equal to the candidate split point P are assigned to the left child node, and those greater than P are assigned to the right child node. Next, we calculate the Gini indices of the left and right child nodes, and then calculate the information gain for this split. Technically, though, information gain refers to entropy-based measures. When using the Gini index, the more accurate terms are Gini gain or Gini impurity reduction. For simplicity, we'll use the term information gain in a broader sense. The first term is the Gini index before the split, and the second term is the weighted sum of the Gini indices of the left and right child nodes after the split. Their difference is the information gain for this split. If the information gain of this split is greater than that of other splits, it is considered the best. Update maxIG with the new information gain. Then, set the current feature ID and split point P as the best feature and split point. Also, store the corresponding left and right child nodes. In the first for loop, the best feature is selected, and in the second for loop, the best split point is selected. After the two for loops finish, if the maximum information gain is greater than 0, it returns the following best split criteria for the current node. If the maximum information gain is less than or equal to 0, we do not split this node. Next, we define a function that generates a binary tree by recursively calling the previous function. We pass the parent node returned by node split to this function and recursively split its child nodes. We stop the recursion when the maximum tree depth is reached. We recursively split the left child node until the maximum depth of the tree is reached. We first split the left child node. If it is not a leaf node, we store the split information and continue splitting it recursively. The same applies to the right child node. Once this function finishes, a binary tree is created. Next, we define a function that finds all leaf nodes in the tree and assigns the majority class to each leaf node. This function takes the root node as input and recursively traverses the tree to find all leaf nodes. If the left node contains only an array of data sample indices, it is a leaf node. Then we assign the majority class label to this leaf node. If it is not a leaf node, recursively continue traversing the tree. Repeat the same process for the right child node. Next, we implement a fit function that builds a tree from the training data. The input X is the feature matrix of the training dataset, and Y contains the target class labels. First, we use the node split function to split the feature data into left and right child nodes. Next, we recursively split each child node using the recursive split function until the tree reaches its maximum depth. Next, we call the assign leaf values function to assign the majority class label to each leaf node. Next, we define a function to predict the class of a single data sample. This function takes the root node and a data sample X as input. It compares the input feature value with the split criterion of the current node. If this condition is true, it moves to the left child node. Otherwise, it moves to the right child node. If the next node is another split node, the same process is repeated recursively. Once the traversal reaches a leaf node containing the final prediction, the predicted class label is returned. Finally, we define a function to predict the class labels for all input samples. We use the predict1 function defined above to predict the class label for each sample one by one. So far, we have implemented the DecisionTreeClassifier class, which is the core component of a CART classification tree. Next, we will import the DecisionTreeClassifier class from the previous slide and use it to classify the Titanic dataset. We will also use scikit-learn's Decision Tree Classifier and check if the two results match well. Load the Titanic dataset and perform basic preprocessing. The preprocessed data looks like this. Split this dataset into training and test sets. Now we build a CART classification tree. We set the maximum depth of the tree to 3 and create a DecisionTreeClassifier instance. We then fit the model to the training data. Next, we predict the class labels for the test data and measure the accuracy. Finally, we use scikit-learn's Decision Tree Classifier to build a CART model. Then predict the classes of the test data and measure accuracy. Then visually compare the trees from the two models. The results are shown below. The accuracy on the test data is the same for both the DecisionTreeClassifier and scikit-learn's Decision Tree Classifier at 0.843. On the left is the tree generated by DecisionTreeClassifier, and on the right is the tree generated by scikit-learn's Decision Tree Classifier. At the root node, the best feature ID is 1. And the best split point is 0.5. At the first left child node, the best feature ID is 2. And the best split point is 13.0. At the second left child node, the best feature ID is 3. And the best split point is 2.5. The first leaf node contains one data sample from class 0 and 14 data samples from class 1. Therefore, its majority class is 1. The same is true for this model. The second leaf node has a majority class of 0. You can see that the results from the two trees match exactly. Now let's run this code. The results are as follows. In this video, we implemented code to build a CART classification tree from scratch. In the next video, we will look at how to evaluate feature importance in decision trees.